So we're going to look at the power simulation here. And this looks a lot like the applet that we've used before, but notice that here you have both the hypothesized probability of success, that's like your null hypothesis, and also the alternative probability of success. So this is like a new level of what if question, because you're asking, okay, what if the true value were really 0.53? What would happen in that case? So we're going to set our null hypothesis with 63%. That's what the percentage you had to wait before the change. And we're going to set our alternative at 0.53, sort of asking what would that look like. We said our sample size was 100. Okay, so let's just start off just looking at the null hypothesis. So this part's going to look really familiar. So I can draw a sample of size 100. And I can see, okay, in that sample of size 100, if the null hypothesis were actually true, I got a sample proportion of whatever that is, 0.73. They have like wrecked this scale. It didn't used to look like this. Obviously, different samples are going to end up with different values, but we would expect it to be centered around 0.63, right? And I can do a bunch of those. Let's just get up to 1,000. Okay. So far, this all looks very familiar. And if you think about when you reject when the p-value is very small, right? So you're going to reject when this is we're looking at a less than test. So we're going to reject for sample values that are like down here, right? So we can actually set it up with the level of significance. I'm going to put in alpha as 0.01. And that's marking that bottom 1%. So this is saying basically if you're below 0.51, if you get a sample proportion that's below 0.51, then you're going to reject the null hypothesis, right? That's like our cutoff for where we would reject. So up until now, this is all we've been looking at. We've just been looking at the null distribution. But now we're going to start asking, okay, well, what if the alternative were really 0.53? How often would we actually be low enough to reject the null hypothesis? That's our question. So I'm going to show the alternative now. So this is still 1,000 samples, but this is 1,000 samples assuming that the parameter was really 0.53, right? And we're looking to see how often in that case was the value low enough for us to reject the null, right? The null really is false. It's 0.53, so it really is lower than our null hypothesis value. And then were we able to reject the null in this case? So kind of bad news here. The chances of us making the right decision are less than half. So our power in this case is only like 39%. That's not good, right? And 100 doesn't even seem like that small of a sample size. But if we look at it, like you can sort of think about these two distributions, there's a lot of overlap, right? If you just see one point, it's going to be kind of hard to tell whether you're talking about the null distribution or the alternative distribution because there's so much overlap in the points, right? So basically the only way we can reject the null is if we end up with one of these values that just happens to be on the low end, right? So that's why our power here is really low. First of all, we're assuming in this one that the null hypothesis is true in this top picture. So we're assuming that pi is equal to 0.63. And just like usual, this is a sampling distribution. So this is showing each dot is a p hat. This is showing all the different sample proportions we would expect to get if the null hypothesis were true. So we're looking at this bottom 1%, right? That's where we're setting our alpha level, and that's helping us set our cutoff. So I'm going to kind of like extend the line up here. So basically anything that is to the left of this line, that's when you're going to reject the null hypothesis. Okay? Anything that's to the left. Whereas anything that's to the right of this line, you're going to fail to reject. And you're setting your cutoff by looking at the bottom 1%. So this is alpha is 0.01, so we're looking at that bottom 1% there. We can also think about what these different sections represent. So this is showing us when the null hypothesis is true. So this red area over here, this is showing us when we would be making a type 1 error, right? Because the null hypothesis is true, but we're on the left side of the line, so we're rejecting the null. So actually, when you set your alpha level, when you set your alpha level as 0.01, you're also setting what's the probability of making a type 1 error. So that sort of makes sense then, that when you make your alpha level higher, it's more likely to make a type 1 error. If you make your alpha level lower, it's less likely. So we're still using this same line, right? You can see that this cutoff goes all the way down, but the assumption is different here, right? Now we're assuming that the alternative hypothesis is true. And we're being specific here. What if it was going down by 0.53? So again, we're going to be rejecting everything that's to the left of the line. Make this a little smaller so you can see it all at once. We're rejecting everything that's to the left of the line, and then we're failing to reject everything to the right side of the line. But in this case, rejecting is what we want to do, right? The null hypothesis actually is false and the alternative is true. And so this green area, this represents power, because this is where we make the correct decision to reject the null when it's really false. Everything on this side, all of this dark area, this is actually the type 2 error. So we can fix this by changing the sample size. So when I change the sample size, what's going to happen to those distributions? Can anybody make a prediction? So thinking about like the shape, center, and spread of those distributions.
The spread would decrease.
Yeah, the spread is going to decrease. So let's do like maybe 300 now. So the spread has decreased a lot. And the nice thing about the spread decreasing is that even though they're still at 0.63 and 0.53, there's not nearly as much overlap anymore, right? So now if we look at that cutoff, the cutoff has changed because the spread has decreased. But if we look at how many are below that cutoff, now it's most of them, right? Now our power is at a little bit over 90%. So I think I had asked a question here. Yeah, how large would the sample size have to be to have power of 90%? And it looks like about 300 will get us there. It could be probably a little bit lower. Okay, so let's think about the other things that we could change here. So what about changing the alpha level? If I make my alpha level higher, so right now it's at 0.01, if I make my alpha level higher, what's going to happen to that picture? How's it going to change? So right now, my alpha level is marking like that bottom 1%, right? So we're looking at that line. If I make my alpha level higher, which way is that line going to move? To the left or to the right?
To the right.
Yeah, it's going to move to the right. And if I move that line to the right, if I move the cutoff to the right, what's going to happen to my power? Is it going to go up or down?
It would go up.
Yeah, it would go up, right? This green area represents the power. So if I move this to 0.05, the cutoff is shifting to the left. We're not requiring as much evidence there. So if you don't require as much evidence, then these values are more likely to cross that line, right? So you're more likely to have enough evidence to reject when you set your cutoff a little bit easier, okay? Okay, so we've talked about sample size. That changes the spread, which can give you less overlap. We talked about alpha. That's going to move your cutoff back and forth. The other thing is how big of a difference it makes. So like, let's say that instead of changing it to 0.53, what if it makes a big difference? What if it goes all the way down to only 33% of people have to wait? So what's going to be affected here? Would that be the shape, center, or spread of that distribution?
Center.
Yeah, the center, because it's centered right now at 0.53. Now it's going to be moved all the way down to 0.33. So at this point, there's very little overlap between these two distributions, right? If you see a point, you pretty much know which distribution it came from because there's such a big difference here. So if I count now, the line is so far away from my actual distribution that the power here has gone way, way up.